6 Bizarre Objects of the Universe. Hello everyone, welcome to my channel. In the depths of the distant universe, there are many strange and bizarre objects that people can't understand. Some of them maybe science fiction writers cannot imagine the strange shape, such as no mother star wandering in the depths of the universe of the stray planets. Some of them, despite the small size, but has a horrible destructive ability, such as binary stars in the Neutron star. There are also some seemingly ordinary, but scientists feel very confused, such as that is often referred to as Tabby Star of the strange objects. The strange star often called Tabby Star. Today, I want to take you to know 6 kinds of strange objects in the universe that make people amazed. In the search for the truth of the universe, we will unveil pages and pages of unknown mysteries. 1. Tramp planet. Wandering planets, as the name suggests, are those planets that wander in the universe without a fixed orbit around any star. While planets in the traditional sense generally orbit a star, such as the Earth around the Sun, wandering planets are not attached to any star. Their formation history can be very colorful, and they may have been expelled from the galaxy during star formation, or they may have formed in interstellar space. The existence of stray planets is actually a relatively new discovery. While early astronomers usually focused on planets that orbit within star systems, the existence of stray planets didn't begin to be confirmed until the early 2000s. At that time, scientists used advanced observational techniques, such as infrared telescopes, to discover these elusive objects. In fact, the first confirmed stray planet was discovered in 2012 and is called CSR 2149-0403. It's much colder than Earth, with a surface temperature of nearly -220 degrees Celsius, making it a real squeaker. Why should we be interested in these lonely stray planets? For one thing, they may give us clues about the evolution of galaxies. Think of them as wanderers in the universe, whose existence and trajectories can help us understand how galaxies form and evolve. In addition, the discovery of stray planets has potential implications for the search for extraterrestrial life. Although they may not be suitable for life, their extreme environments and isolation have piqued scientists' curiosity and prompted us to re-examine the conditions for life. As an example, scientists have hypothesized that if a stray planet has enough heat inside it, liquid water may exist, thus providing some possibility for life to survive. So, what are the basic characteristics of a stray planet? First, let's talk about the physical characteristics of these stray planets. Simply put, stray planets are similar in appearance to our own Earth, but their size and mass can vary greatly. Some stray planets may be as small as a marble, with a mass about the same as one of Saturn's moons, while others are as massive as Jupiter, and may even have a mass greater than some of the planets in our solar system. For example, the stray planet CSR 2149-0403, discovered by astronomers, is about the mass of Jupiter and about the same diameter. Its mass can range from a few to several tens of times that of Earth. The size and mass of these planets have a great impact on their environment and composition. Then there is the surface temperature. The temperatures of stray planets can be extreme, depending largely on their composition and formation history. For example, stray planets that have been away from their stars for a long time tend to have very low surface temperatures, some even close to absolute zero, -273 degrees Celsius. This sounds a bit like a refrigerator in a freezer, but it's a common phenomenon in the universe. As for composition, the interiors of wandering planets may include rocks, metals, and gases, depending on how they were formed. Similar to planets in star systems, the composition of stray planets may include gases such as hydrogen, helium, and methane, but their proportions and distribution vary depending on the planet's formation history. The most striking feature of wandering planets is their orbits. They are literally free-roaming loners. These planets have no fixed orbits, which means they don't orbit any one star. It's like walking around a busy city without any constraints. Scientists have found that stray planets have very irregular orbits, and some even travel through interstellar space. For example, scientists once discovered that a stray planet's orbit was severely distorted as it approached a galaxy far from Earth, a situation that provides valuable information for our study of the interstellar medium and gravitational effects. The formation mechanism of stray planets is actually quite interesting. We can understand the birth of these objects from several angles. First, we have to understand the basic theory of planet formation. Most planets form in protoplanetary disks, those disks of gas and dust that revolve around newborn stars. In these disks, dust particles gradually gathered and eventually formed planets. However, the mechanism of formation of wandering planets may be different. There are several major theories that explain their birth. One theory is that stray planets may have originally formed from protoplanetary disks. Just like other planets, these stray planets may have been born around a star. However, their fates are different. Scientists have found that some stray planets may have experienced extreme environmental changes during their formation, causing them to eventually be thrown away from their original star systems. As an example, a 2016 study suggests that after a large number of planets form in certain young galaxies, those planets that aren't fully attracted could be thrown out of the galaxy due to gravitational forces. In other words, planets that were originally part of a particular star system may have become lonely wanderers after a series of gravitational effects. Another theory is that stray planets may have originated from other star systems. This is like a cosmic capture game. In this case, a stray planet drifting through interstellar space could be gravitationally captured by another star, creating a new orbit. Imagine a giant gravitational net that captures these stray planets in interstellar space. This scenario is actually not that uncommon in the universe. Using observational data, scientists have found that there are stray planets among the stars whose orbits show clear signs of gravitational interference. So why do planets escape their original orbits and become stray planets? It comes down to several factors to consider. The escape of stray planets is often associated with gravitational disturbances in the star. If there's some drastic gravitational change in a star system, such as two massive planets in close proximity, their gravitational forces can interact and cause other planets to be thrown from their original orbits. It would be like if you were walking around and suddenly bumped into a friend, and both of you could be knocked apart. Gravitational interactions between planets can also lead to the escape of planets. If a planet comes close to another massive planet in a system, the gravitational interaction between them could push the third planet into interstellar space. Scientists have found through simulations that this is very common in some young galaxies. 2. Neutron stars. When it comes to neutron stars, let's first look at the evolution of a massive star. First, we need to know what a massive star is. How heavy does a star have to be called massive? Typically, we're talking about stars that are at least 8 times the mass of the Sun. These massive, shining stars are destined for a unique journey from the very beginning. Imagine a nebula in the universe, the maternity ward of a star. These nebulae are made up of large amounts of gas and dust, the main component of which is hydrogen. These nebulae begin to coalesce when some external force, such as a nearby supernova explosion or the gravitational collapse of the nebula itself, causes them to collapse. That's when the star starts to budge. For example, just like the birth of life on Earth, the birth of a star in the universe is a gradual process. At this time, the gas and dust in a nebula begin to gather and form a dense sphere, which is called a pre-main sequence star. Over time, the temperature and pressure at the center of these pre-main sequence stars increase, eventually triggering the hydrogen fusion reaction that gives rise to stars. Once a massive star is born, it rapidly reaches adolescence, and its nuclear reactions are quite violent. Instead of burning for billions of years, as the Sun does, these stars consume the hydrogen fuel in their cores at a very fast rate. Their internal temperatures and pressures are so high that heavier elements, such as helium, carbon, and oxygen, are produced, which in turn undergo a series of nuclear fusion reactions. At this time, massive stars are a classic example of adolescent rebellion. They shine brightly, releasing large amounts of energy all the time. Such glory days for them are quite short, only a few million to tens of millions of years, compared to the lifespan of the star, which is like a moment in time for us humans on Earth. In the cores of massive stars, heavier and heavier elements are synthesized over time as nuclear fusion continues. Eventually, the cores of these stars cross over into a phase called iron. What's so special about iron, you may wonder? Iron is an element that can't undergo nuclear fusion to release energy. When a star's core turns to iron, it is running out of fuel. As astronomers say, iron is the end of the line for massive stars. The star can no longer generate enough energy through nuclear fusion to support its own gravity, leading to a series of tragic endings. When the iron core at the center can't support the star's thick shell, it undergoes a massive collapse, producing a violent reaction. The rapidly collapsing iron core rebounds, triggering a massive supernova explosion. This is truly a cosmic fireworks display, as the star ejects huge amounts of matter and energy in a violent explosion. The explosion is not only a glorious end to the star, but also an important prelude to the formation of the next generation of stars and planets. As Carl Sagan said, we are all made of stardust. The material left over from these explosions, including heavy elements, will be the building blocks of future nebulae and planets. Neutron stars are a product of supernova explosions. They are formed from the core left over from a supernova explosion. Because this core is very small, it is extremely massive. The density of neutron stars is extremely impressive. You can imagine it this way: compress the entire mass of the sun into a small ball that's only about 20 to 30 kilometers in diameter, and that kind of material becomes a neutron star. To visualize the concept even more, if you could take a small spoonful of neutron star matter out, that small spoonful would have a mass roughly equal to all the mountains on Earth combined, if not more. This means that the density of matter in neutron stars is simply beyond imagination. In fact, how dense is a neutron star? Scientists' calculations show that the density of neutron stars can reach billions of tons per cubic centimeter. It's like taking an ordinary object and compressing it to such an extreme that the particles almost stick together to form a super compact object. The reason this density of neutron stars is so high is because they are made up mostly of neutrons, which are spaced extremely close together, thus making the matter extremely dense. Now for gravity. The gravity of neutron stars is also extremely strong. The fact that they have a lot of mass but are small in size results in an unusually strong gravitational pull. If you could stand on the surface of a neutron star, the gravitational force would be hundreds of millions of times that of the Earth, which would make it almost unbearable to be in that environment. The strong gravity of a neutron star also affects the space and time around it. For example, Einstein's theory of general relativity tells us that the stronger the gravitational field, the slower time passes. In an extreme gravitational environment such as a neutron star, the difference between the passage of time and how we feel it on Earth can be enormous. This strong gravitational force affects not only objects, but also the path of light. Light near a neutron star is bent by gravity, an effect known as the gravitational lensing effect, meaning you may see light being bent in an exaggerated way. In addition, this strong gravitational pull can lead to a phenomenon known as tidal forces. The gravitational pull of a neutron star on the material around it not only draws material to its surface, but also produces a violent tidal effect that causes the material on the star's surface to change dramatically. This also leads to the possibility of an extremely hot ring of radiation around the neutron star, which carries powerful electromagnetic energy and can emit extremely intense radiation that we can observe. Neutron stars are truly a marvelous cosmic mystery. First, a word about the surface of a neutron star. Imagine what your surroundings would be like if you were standing on a super-compressed object. The surface of a neutron star is extremely cool and extremely hard. Although its surface temperature is usually around a few million degrees, it's still much cooler than the temperature inside. Because of its strong gravity, there may be an extremely thin shell on the surface, formed by residual material on the surface of the neutron star, mainly iron and other heavy elements. This shell would be so hard that it might appear to be composed of a huge piece of super strong metal. In fact, the surface gravity of a neutron star also makes almost any ordinary material extremely dense, so it would be difficult to analogize the surface to materials on Earth. Interestingly, the surface of a neutron star may also have strong magnetic fields that are strong enough to cause surface material to produce enormous amounts of electromagnetic radiation. In fact, this strong magnetic field creates so-called magnetic poles that emit strong electromagnetic waves from the poles of the neutron star, which is one of the reasons why pulsars glow. Next, let's talk about the internal structure of neutron stars. The interior of a neutron star is arguably one of the strangest places in a universe. The core of a neutron star is extremely dense, and its matter is composed almost entirely of neutrons. Scientists hypothesize that these neutrons may form a state called superfluidity in the core. A superfluid is a special state of matter that can flow without any resistance. Imagine that water has a certain viscosity on Earth, while superfluidity is like water without viscosity, which is like flight without resistance in the world of fluids. In the core of a neutron star, there may also be a state of superconductors. A superconductor is a material in which, at very low temperatures, the resistance of the material completely disappears, allowing electric current to flow through it indefinitely. In the case of neutron stars, this state may allow the magnetic field and electric current inside to be maintained for very long periods of time without energy loss. This property is important for understanding the magnetic field and rotation of neutron stars. Scientists have also proposed an interesting theory that the core of a neutron star may contain a structure called a quark star. A quark star is a denser object than a neutron star, and its core may be made up of quarks, elementary particles smaller than neutrons. Although this quark star has not yet been directly observed, it is an interesting area of study for scientists. In addition to the hard outer shell of a neutron star, there may be a region called the gravitational wave layer. The gravitational wave layer refers to the weak gravitational waves generated by the neutron star's extremely strong gravitational field, which can be transmitted to the outer layers of the star and have an effect on the surrounding universe. This gravitational wave layer is very weak, but its existence and role are of great significance to the study of the physical properties of neutron stars. 3. White dwarfs. White dwarfs are an endpoint in the life cycle of a star, literally like the retirement of a star. Stars are like giant energy factories whose fuel is hydrogen and helium. In their early years, stars undergo nuclear fusion at their cores, which converts hydrogen into helium and produces a lot of energy. Like the sun, we can think of it as a young, energetic factory operating at a steady pace. But over time, stars run out of fuel and their life cycles change. When a star's core is almost out of hydrogen fuel, it goes through a series of changes. First, it expands into a red giant. At this stage, the star's outer shell becomes so inflated that it resembles a giant balloon. The red giant is much larger than it was when it was young, and this is when its brightness increases. However, red giants don't have long to live, as they go through what is known as the shell detachment phase. During this process, the star's outer layers of gas are thrown out into cosmic space, leaving only the core. This core is the white dwarf we're talking about today. You may ask, what is the difference between a white dwarf and a neutron star, given their similar formation process? The difference is that white dwarfs form for stars that are less massive, like the Sun. Neutron stars, on the other hand, form for a star that is much more massive than the Sun. Neutron stars are much denser than white dwarfs. Imagine a teaspoonful of neutron star material, which weighs as much as millions of Eiffel Towers on Earth. A white dwarf is the end result of the evolutionary process of a red giant star and is a very compact and dense core of stars. It has about 0.6 times the mass of the Sun, but is only about the size of the Earth. In short, it's like compressing a giant sun into a tiny sphere. For example, there's a famous white dwarf called Sirius B. It was once an ordinary star. It used to be an ordinary star, but now it is the size of the Earth and nearly half the mass of the Sun. The story of Sirius B is fascinating because its companion star, Sirius A, is also very well known and is one of the brightest stars in the night sky. The study of this binary star system has helped us better understand the nature of white dwarfs. So why do white dwarfs have such high densities? Well, it's thanks to an amazing phenomenon called electron merger pressure. Let me explain. In an ordinary star, the pressure comes mainly from the energy generated by thermonuclear reactions, which supports the star's massive size. However, by the time a star evolves to the white dwarf stage, the nuclear fuel has been exhausted and the core temperature has dropped dramatically. At this point, it is no longer the thermal pressure that supports the star, but the electron merger pressure. The electron merger pressure is generated by quantum mechanical effects. According to the bubble-A incompatibility principle, electrons cannot occupy the same quantum state. Thus, when the core of a star is compressed to an extremely high density, a strong repulsive force is generated between the electrons, which is called the merger pressure. It resists further gravitational compression and maintains the stability of the white dwarf. A particularly interesting true story is that in 1930, at the age of 19, the Indian physicist Subramanian Chandrasekhar was on a ship bound for Cambridge University in England when he calculated the upper limit of the mass of a white dwarf star, which became known as the Chandrasekhar limit. His mentor at the time, Arthur Addington, did not believe the young man's calculations at first, and even questioned him in public. However, Chandrasekhar was proved right, and he was awarded the Nobel Prize in Physics in 1983. The density of white dwarfs can be as high as several tons per cubic centimeter or even more. As an example, a teaspoonful of white dwarf material can weigh tens of tons, equivalent to the weight of several elephants. This extremely high density makes white dwarfs one of the densest objects in the universe. Another thing you might wonder is why white dwarfs are so hot. Although it no longer undergoes nuclear fusion, due to the amount of energy it accumulated during its red giant phase, it is still very hot, often reaching temperatures of 10,000 to 100,000 degrees Celsius. However, due to its small size and small radiation area, it will eventually cool down and become fainter and fainter. Interestingly, the temperature change of white dwarfs is a very long process. Although they cool slowly, the process can last for billions of years. White dwarfs gradually change from a hot blue-white color to a cooler red color over time, until they eventually become dim and become black dwarfs. However, because the universe isn't old enough yet, we haven't found any true black dwarfs yet. As an example, the famous white dwarf Sirius B, which is the companion star of Sirius A. The star has a surface temperature of about 1,000 degrees Fahrenheit and a surface temperature of about 2,000 degrees Fahrenheit. Sirius B has a surface temperature of about 25,000 Kelvin, and although it has cooled considerably, it is still very hot. Astronomers have learned a lot of details about the cooling process of white dwarfs by observing this white dwarf. In addition, white dwarfs play an important role in the age determination of the universe. You see, white dwarfs are the end stage of a star's life. When stars run out of nuclear fuel, they shrink into white dwarfs and begin to cool gradually. This cooling process is very long and can last billions of years. Scientists have found that by measuring the temperature and brightness of white dwarfs, their age can be estimated. Because white dwarfs no longer undergo nuclear reactions once they are formed, and there is only a cooling process, the rate at which their temperature drops is relatively constant. There is a method called the white dwarf cooling age method that astronomers use to estimate the age of the oldest stars in the Milky Way. By observing the temperature and brightness of these old white dwarfs, scientists can back out their cooling time and thus estimate their formation time. This time, plus the time of stellar evolution before the white dwarfs formed, is the age of the Milky Way. The study suggests that our Milky Way is about 13 billion years old, a figure that is crucial to understanding the formation and evolution of the universe. Interestingly, scientists have found many planetary debris and dust disks around white dwarf stars. These debris and dust disks may have formed when protoplanets were destroyed during stellar evolution. These discoveries provide an excellent opportunity to study the evolution of planetary systems over long periods of time. As an example, the famous white dwarf WD 1145 plus 017, whose light curve shows periodic decreases in brightness, suggests that material has passed in front of the white dwarf. Further observations revealed that the material may have consisted of a disintegrating planet or asteroid. This discovery allowed scientists to directly observe the evolution of planetary systems during the white dwarf phase. In addition, the gravitational field of a white dwarf is so strong that it can capture and tear apart asteroids or comets that come close to it. By studying this torn material, scientists can learn about the composition and evolutionary history of planetary systems. For example, by analyzing the elemental content in the atmospheres of white dwarfs, scientists have found some Earth-like material, suggesting that these white dwarfs may once have had Earth-like planets. 4. Brown dwarfs. Brown dwarfs, you can think of them as unfinished stars between stars and planets. The name sounds a bit strange, doesn't it? Actually, the mass and properties of brown dwarfs do make them a bit awkward, because they are neither stars nor planets, but something in between. To understand brown dwarfs, let's talk about the basic concepts of stars and planets. Stars, such as our Sun, are those objects that are capable of nuclear fusion reactions. The internal pressure and temperature of a star is so high that it is able to fusion hydrogen atoms into helium atoms, releasing a lot of energy. It is this energy that allows stars to shine and become the beacons of the universe. Planets, such as the Earth, are celestial bodies that orbit a star. Planets don't have enough mass or internal pressure to undergo nuclear fusion, so they don't shine on their own, but reflect the light from the star. Planets usually have much less mass than stars. So, what exactly are brown dwarfs? Brown dwarfs have a mass somewhere between that of a star and a planet, about 13 to about 80 times the mass of Jupiter. This mass range is important because it determines the fate of brown dwarfs. Objects less than 13 times the mass of Jupiter are incapable of any form of nuclear fusion and can only be planets. Objects with more than 80 times the mass of Jupiter, on the other hand, are able to undergo nuclear fusion of hydrogen and become true stars. Here's a bit of science. Jupiter is about 318 times the mass of the Earth. That is, if you add the mass of 318 Earths together, it's almost equal to the mass of one Jupiter. Because of the mass of brown dwarfs between stars and planets, they can undergo nuclear fusion of deuterium, an isotope of hydrogen, but this reaction is very short-lived. Because they cannot sustain prolonged nuclear fusion, brown dwarfs do not shine steadily like stars, but gradually cool and dim. In 1988, astronomers discovered an object called Tide 1, which did not resemble a typical star in mass or brightness. After careful study, scientists confirmed that it was a brown dwarf star. This discovery led to a deeper study of brown dwarfs. Scientists found that brown dwarfs also have unique spectral characteristics. Because they are cooler than stars, their spectra show absorption lines of molecules that are not seen in the spectra of stars, such as water vapor and methane. By studying the spectra of brown dwarfs, astronomers are able to better understand their composition and evolution. The discovery and history of brown dwarfs is actually a very interesting bit of science. First, go back in time to the 1960s. At that time, scientists began to wonder if there were some objects in the universe that were somewhere between stars and planets. Stars are those massive objects that can glow and heat up through nuclear fusion reactions, while planets are less massive objects that orbit stars. So, could there be a type of object that is not massive enough for a sustained fusion reaction, yet heavier than the average planet? This is when theoretical physicists came up with the concept of brown dwarfs. Although such objects existed in theory, it was not easy to find them. It wasn't until the 1990s, with advances in astronomical observation technology, that scientists were finally able to search for these mysterious objects in the vastness of the universe. In 1995, on the Spanish island of Tenerife, astronomers using the Gaia telescope discovered an exceptional object, TID 112,255 to 113,343, whose spectral characteristics and brightness differed from those of typical stars. Further observations confirmed that this was none other than a brown dwarf star. Almost at the same time, another brown dwarf, Theta 1, was also discovered. Located in the Taurus cluster, Theta 1 is about 55 times the mass of Jupiter and has a very low luminosity, making it almost imperceptible. The discovery of these two brown dwarfs marks the moment when astronomers have finally confirmed the existence of this class of objects observationally. There is an interesting tidbit about Theta 1. At the time, astronomers were observing the Taurus cluster when they noticed a point of light that was much fainter than the other stars in the cluster. At first, they thought it might be a distant star or some kind of instrumental error. However, after careful analysis, they discovered that the object's spectrum contained a large amount of lithium. Lithium is rapidly consumed inside a star, so it is almost non-existent in ordinary stars. Brown dwarfs, on the other hand, retain large amounts of lithium due to their inability to undergo prolonged nuclear fusion. This discovery serves as an important piece of evidence to confirm that Theta-1 is a brown dwarf. Another expert on brown dwarfs, astronomer Jill Tarter, has said, "The discovery of brown dwarfs not only confirms our theoretical predictions, but also gives us a deeper understanding of the process of star and planet formation." Tarter's research points out that brown dwarfs form in a similar way to stars, but are not massive enough to ignite a sustained fusion reaction. Now let's talk about how brown dwarfs form. Actually, brown dwarfs form in a very similar way to stars. They both originate in nebulae, the giant clouds of gas and dust in the universe. You can think of nebulae as giant cosmic nurseries where all kinds of objects are born. In nebulae, certain regions begin to collapse due to their high mass. This process is due to gravity and is similar to grabbing a clump of sand in your hand on the beach, where the sand collects in your hand. As this gas and dust continues to gather, the temperature and pressure at the center gradually increases. However, the key difference between a brown dwarf and a star is mass. Stars are massive enough that the temperature at the center can reach millions of degrees or more, which ignites a hydrogen fusion reaction. This reaction converts hydrogen into helium, releasing a huge amount of energy that makes the star glow and heat up. But brown dwarfs aren't so lucky. They are typically between 13 and 80 times the mass of Jupiter, a mass range that, while larger than the planets, is not enough to ignite sustained hydrogen fusion. In other words, brown dwarfs have too little mass to sustain a nuclear reaction like that of a star. There have been many interesting studies and discoveries about the formation and evolution of brown dwarfs. Astronomer Adam Burge's research on brown dwarf states, brown dwarfs are like ghosts in the universe. They wander between stars and planets and, although not easy to spot, reveal a lot of secrets about star formation. The gravitational pull of brown dwarfs is quite strong, largely due to their relatively large mass. Imagine if you were on the surface of Jupiter, you would feel a strong gravitational pull. Brown dwarfs have even stronger gravity than Jupiter because of their greater mass. This strong gravity makes brown dwarfs very dense. Simply put, the material in brown dwarfs is compressed very tightly. For example, if you were to compress the mass of a brown dwarf into the volume of the Earth, it would be denser than any known material. This dense structure is also why brown dwarfs are not ridiculously large despite their large masses. Brown dwarfs have the same main components as stars, mainly hydrogen and helium. They absorb large amounts of hydrogen and helium from nebulae during their formation. These are the most common elements in the universe, so it's no surprise that they dominate brown dwarfs. As we mentioned earlier, brown dwarfs don't have enough mass to ignite sustained hydrogen fusion. This means that the temperatures and pressures inside brown dwarfs, while high, are not enough to sustain nuclear reactions like those in the Sun. This also led to the gradual cooling down of brown dwarfs after a brief period of deuterium fusion early in their formation. Without a sustained nuclear reaction, brown dwarfs can only rely on their own heat to slowly dissipate, gradually becoming darker and colder. The atmospheres of brown dwarfs are filled with a variety of complex molecules. This is another significant difference between them and stars. Due to the lower temperatures, some molecules can exist in the atmospheres of brown dwarfs that cannot exist in stars. For example, carbon monoxide, CO, methane, CH4, and water vapor, H2O, are very common in the atmospheres of brown dwarfs. These molecules can reflect the temperature and chemical environment of brown dwarfs to some extent. As an example, astronomers have found through spectroscopic analysis that the atmospheres of some brown dwarfs contain large amounts of methane, indicating that these brown dwarfs have relatively low temperatures. There are many interesting studies and stories about the physical properties and internal structure of brown dwarfs. Astronomer Jill Tarter once said, The atmospheres of brown dwarfs are like chemical laboratories filled with all sorts of wonderful molecules. These components not only help us understand brown dwarfs themselves, but also give us a deeper understanding of chemical processes in the universe. At one point, Tate and her team were observing a brown dwarf star when they noticed large amounts of carbon monoxide and water vapor in its atmosphere. This discovery excited them because it meant they had found a natural laboratory where they could study complex molecules. In addition, even small brown dwarfs can form large-scale weather systems. For example, the researchers found that the atmosphere of the T-type brown dwarf BD plus 012920b has a huge storm system with wind speeds of thousands of kilometers per hour. The L-type brown dwarf SDSS, on the other hand, shows periodic variations in brightness, which may result from thick clouds in the atmosphere reflecting light at different angles. These findings are reminiscent of gas giants like Jupiter and Saturn. Although brown dwarfs are only about 1/10 the size of Jupiter, their atmospheric dynamics may share many similarities. For example, the NASA Juno probe has observed rotational changes in cyclonic storms on Jupiter that are somewhat similar to the periodic changes in brightness observed in the atmospheres of brown dwarfs. Such studies will not only help us better understand the structure and properties of such peculiar objects as brown dwarfs, but also provide valuable references for understanding the atmospheric evolution of distant exoplanets. Let's talk about the temperature and luminosity of brown dwarfs. It is well known that these objects have a wide range of surface temperatures, from a few hundred Kelvin to a few thousand Kelvin, with L-type brown dwarfs usually warmer, up to about 2000 Kelvin, while T-type brown dwarfs are generally cooler, with temperatures of only about 1000 Kelvin. This temperature difference is mainly due to differences in the chemical composition of their atmospheres. For example, L-type atmospheres have more dust and metal hydrides, while T-type atmospheres are rich in methane and water vapor. These temperature differences also directly affect the luminosity of brown dwarfs. Although they may have a surface area comparable to that of the Sun, they radiate only about 1/millionth of the total energy of the Sun because of their lower temperatures. Most of the radiation is concentrated in the infrared band, making them invisible stars. This characteristic makes it necessary to rely on highly sensitive infrared instruments when searching for and observing brown dwarfs. When it comes to the significance of brown dwarfs, the first person to mention is Professor Adam Krauss, who is one of today's leading experts on brown dwarfs. Professor Krauss believes that these peculiar objects, which lie between planets and stars, can provide an excellent bridge for us to observe and understand the formation mechanisms of these two types of objects. Brown dwarfs are like a funnel in the evolution of the heavens, he once said, and they can help us better understand how stars form and how planets coalesce out of primordial nebulae. That's a really enlightening point of view. We know that the processes of planet and star formation are fundamentally different, but in some ways they are related. Brown dwarfs are like a transition between these two types of objects. They have a stellar mass, enough to support fusion reactions, but are too small to burn as steadily as stars. This unique position makes brown dwarfs a good entry point for exploring the hybrid origin of stars and planets. For example, by studying the internal structure and atmospheric evolution of brown dwarfs, we can better understand the material and energy transformations that occur during star formation, and how they affect the formation of companion planetary systems. Conversely, the study of how brown dwarfs gradually coalesce from primordial nebulae can also provide important clues to our understanding of the general pattern of planet formation. This two-way revelation makes brown dwarfs one of the most interesting objects for astrophysicists to study. 5. Tabby Star. Have you ever heard of Tabby Star? Actually, the official name of the star is KIC 846-2852, but everyone likes to call it Tabby Star because the astronomer who discovered it is called Tabitha Briagian. Did you know? The story of Tabby Star actually began in 2015. At the time, scientists were analyzing data from the Kepler Space Telescope, looking for stars that might have planets around them. Suddenly, they noticed that Tabby Star had a very different light variation curve. Instead of being stable like other stars, it showed large fluctuations in luminosity. Imagine suddenly having a light in your room that fluctuates in brightness, not just because of the switch, but perhaps even because of the strange behavior of the bulb itself. The magnitude and frequency of the star's light fluctuations are so large that it feels like something mysterious is blocking its light. The discovery of Tabby Star has attracted a lot of attention from the scientific community, and there is a lot of speculation. What is interfering with the star's light? Tabby's home address is actually in the constellation of Eagle, about 4,600 light-years away from Earth. That's a long way away, and it would take 4,600 years for light to reach Earth from there. But even though it's far away, its story is very dear and fascinating to us. The spectral classification of the star is F-type. Simply put, F-type stars are a class of stars that are slightly hotter and brighter than the Sun. You can think of it as a kind of superbrother that is hotter and brighter than the Sun. Its surface temperature is between 6,000 and 7,500 degrees Celsius, a little warmer than that of the Sun. As for its brightness, Tabby Star is about 100 times brighter than the Sun in absolute terms. Mind you, that kind of brightness isn't particularly rare in the galaxy, but it's its light variable behavior that makes it a conversation star. A light variation curve is a graph that records the intensity of starlight over time. Under normal circumstances, we would expect that changes in starlight should be smooth, similar to looking at stars outside at night, where their light doesn't suddenly disappear or become unusually flickering. But Tabby Star's light variation curve is like a supersized box of surprises. Scientists analyzing data from the Kepler Space Telescope found that the star's luminosity varies extremely irregularly. Instead of remaining stable like most stars, it undergoes a series of huge fluctuations in luminosity. Most notably, there were several significant drops in luminosity between 2011 and 2013, when Tabby's light would plummet by up to about 20% and then return to normal levels. The magnitude and duration of these variations make it seem as if some mysterious force is playing with the star's light. You know what? This unusual variation in light is very exciting for many scientists because it could mean that we have discovered an astronomical phenomenon that we have never seen before. The various explanations for Tabby Star are imaginative and fun to explore. Let's start by talking about some of the more common natural astronomical phenomena. Scientists have considered a variety of natural phenomena to explain Tabby's mysterious light changes. For example, the swirling interstellar dust cloud is a compelling explanation. Imagine you see a huge dust cloud in the night sky that is slowly rotating. It's large enough to block out some of the starlight. It's as if you were on a sunny day and suddenly a cloud drifted by and blocked out the sunlight. This dust cloud can block out some of the light from Tabby Star, causing a drop in the luminosity we see. Scientists have used this explanation for the unusual drop in Tabby Star's luminosity. Astronomer Joseph Lee of Harvard University has mentioned a similar idea, arguing that these interstellar dust clouds could be blocking out starlight on relatively long timescales, leading to changes in luminosity. However, there are limitations to this explanation, as scientists still need to find evidence of the existence of specific dust clouds. Some scientists have proposed the hypothesis of a comet swarm. This hypothesis is actually somewhat plausible. Imagine if a large swarm of comets accompanied by large amounts of dust and debris passed by Tabby Star. That could indeed lead to great variability in its luminosity, a possibility explored in detail in a paper published by Boyajian and her team in 2016. The problem, though, is that the number of comets required to account for such observed luminosity variations is truly astronomical. It's almost like a comet parade across the universe, and the explanation seems a bit far-fetched. Next, it was suggested that perhaps these light changes are caused by the remnants of some larger star or planet. These remnants might orbit Tabby Star in an extremely complex way, causing changes in its luminosity. American astronomer Bradley Schaefer suggested in 2016 that the star might be being surrounded by a toroidal accretion disk, a disk of material that irregularly blocks out stellar light. Although convincing, further observation and confirmation of the evidence is needed. Of course, how can we talk about highly imaginative hypotheses without mentioning alien civilizations? American astronomer and science writer Jason Wright, among others, has proposed that the light variable phenomenon in Tabby Star could be caused by giant structures, such as Dyson spheres, built by an alien civilization. Such structures collect stellar photons to provide energy for higher civilizations to use. Although it sounds very sci-fi, it is undeniable that this hypothesis did attract a lot of attention and even triggered the SETI, Search for Extraterrestrial Civilizations, project to conduct a special listening session on the star. However, it is important to emphasize that so far there is not enough evidence to support this hypothesis of an extraterrestrial civilization. As science writer Phil Plait puts it, we must strive to rule out all other possible natural explanations before making such a bold hypothesis. Recent studies, on the other hand, tend to suggest that this light variation phenomenon could be caused by a massive dust cloud. In 2018, astronomer Boyajian and his team of researchers published a paper stating that the light variation signature of Tabby Star is more consistent with a model of being obscured by dust. Unlike obscuration by large planets or large structures, dust particles can cause the star's light to show a different pattern of attenuation at different wavelengths of the part of the star's light through different filtering effects. To date, the light variation phenomenon of Tabby Star remains as unresolved as an unsolved mystery. Each hypothesis has its supporters and opponents, and we can only gradually solve this mystery through continuous observation and data collection. 6. Pulsars. As you know, the discovery of pulsars is actually attributed to British astronomer John Burnell. In 1967, he was working on a research project on cosmic rays at Cambridge University. One day, he discovered a very peculiar radio source, one that emitted electromagnetic pulses with such precision and regularity that it was hard to believe. At first, Burnell and his colleagues were so perplexed by the source that they suspected it might be a signal from an alien civilization. At that time, some scientists put forward all kinds of strange speculation, such as this may be the alien aviation beacon, and so on. It was only later, after further observations and analysis, that they determined that the signals were actually coming from a completely new type of object, a mysterious object that came to be known as a pulsar. This was a very exciting discovery indeed. The discovery of pulsars not only opened up a whole new field of research, but also revolutionized our understanding of the universe. How are these highly regular electromagnetic pulse signals generated? Where did they come from? These questions have always puzzled astronomers at that time. Pulsars are indeed a very interesting type of object. The first thing to say is that pulsars are actually a special form of neutron star. Neutron stars are extremely dense objects that form when massive stars explode and collapse when they die. The density of these objects is so high that it rivals the density inside the nucleus of an atom. It's the equivalent of compressing the entire Earth to just 10 kilometers across. Pulsars, as the name suggests, are a special type of neutron star that rotate very fast and emit periodic pulses of electromagnetic radiation. These pulsars usually rotate dozens or even hundreds of times per second, emitting regular pulses of electromagnetic radiation like a giant, interstellar lighthouse. These pulsars are able to emit such stable electromagnetic pulses because of their highly dense magnetic fields and extremely fast rotation speeds. It is estimated that the surface magnetic field of some pulsars can reach tens of billions of Tesla, which is already millions of times more than what can be produced in human laboratories. This extreme environment also allows pulsars to emit intense electromagnetic radiation and exhibit periodic pulses as they rotate at high speeds. Because of these unique properties, pulsars play a very important role in astronomical research. They have been used as excellent probes for studying dense astrophysics, gravitational wave detection, and many other frontier fields. For example, by observing pulsar signals, we can accurately determine their rotational periods and thus infer the nature of their internal structure and composition. The rotational stability of some pulsars is even comparable to that of atomic clocks, which makes them very accurate cosmic clocks. In addition, pulsars provide us with an excellent opportunity to detect gravitational waves. Gravitational waves are ripples in space-time predicted by Einstein's theory of general relativity, and they can affect the timing of pulsar pulses. By carefully measuring these variations, we may be able to directly detect the presence of gravitational waves, which is important for verifying the theory of general relativity and exploring the deeper mysteries of the universe. Now let's talk about how pulsars form. Did you know? Massive stars go through many different stages in their lives, culminating in a violent supernova explosion. During this process, a violent fusion reaction occurs inside the star, building up a large number of iron cores. Once the mass of the iron nuclei increase to more than the critical value of the iron nuclei to stabilize the existence of the entire star will begin to sharply contract, self-destruction. At this time, a large amount of gravitational energy will be released, driving the outer material of the star to expand rapidly, forming a supernova explosion. After the explosion, the enormous gravitational compression inside the star causes the originally massive star to shrink into a small, dense object, a neutron star. The density of this neutron star is so high that it is like compressing the entire Earth into a small ball with a diameter of only 10 kilometers. In this extremely dense environment, protons and electrons inside the nucleus of an atom combine to form neutrons, forming an object made of neutrons. A small fraction of these neutron stars retain their powerful rotation speeds and magnetic fields after a supernova explosion, forming what we know as pulsars. These pulsars are known as cosmic lighthouses because of their extremely fast rotation speed, some of which can rotate hundreds of times a second, and their strong magnetic fields, which emit regular electromagnetic pulse signals. So, what is the significance of pulsar research? It's a lot of things. First of all, pulsars provide us with the opportunity to study extreme physical conditions. Neutron stars are extremely dense. By studying pulsars, we can gain insight into how matter behaves under extreme pressures and densities, which is a huge boost to physics. In addition, pulsars are precision clocks in the universe. Because they rotate at such a steady rate, scientists can use pulsars for time measurement and navigation. For example, NASA has considered using pulsar navigation to help future deep space exploration missions. This type of navigation, called pulsar navigation, can provide spacecraft with accurate position and time information in the absence of GPS signals. Pulsar research has its share of cutting-edge problems and challenges. For example, scientists have been exploring the structure and evolution of pulsars' magnetic field. The magnetic field of pulsars is extremely powerful, but the mechanism of its formation and change is still a mystery. What's more, the radiation mechanism of pulsars is also a hot research topic. Although we know that the electromagnetic waves emitted by pulsars come from their magnetic poles, the specific radiation process still needs more observations and theoretical studies to explain. Speaking of challenges, the difficulty of detecting pulsars has to be mentioned. Because pulsars emit very weak signals, capturing them requires very sensitive radio telescopes. For example, the Arecibo radio telescope in Puerto Rico was an important tool for pulsar research, but unfortunately, it collapsed in 2020. Luckily, there are other radio telescopes around the world that are picking up the slack. Well, that's it for this installment. Feel free to like and comment. Thanks for watching.